Yes, Anurag. You can modify the Java code in homework 2 to handle integer overflow. Actually, if I'm right, I thought I asked to try out for various values of a. Okay, so uh, and report the times. Okay, so you can modify the Java code in homework 2. Actually, just the argument a that you have to pass, it changes. That's all. No? Oh, no, you should try to see what is the point of that homework. We should try different values of a and compare what is the performance given with and without hotspot compilation. Okay, if you just get integer overflow, what's the point of doing that exercise? Okay, so you try different values of a and show no. So this is the value of a for which there is no integer overflow happening, and this is the hotspot execution time, and this is the execution time without hotspot enabled. Okay. Okay, let's get started. Time now is 10:35. Segmentation fault while compiling using LLVM for polybench. You can report that, Ananya, that there is a problem in compiling this particular benchmark using LLVM. Sanjana says there is no, okay. Yeah, so yesterday what happened is I was doing multiple things, looking at last year's model, this year's model, and in that process, I sent a mail to the last year's model, last year's class, that the course has been migrated to OpenIndex. But having said that, I automatically added all of you to the OpenIndex. So that means you should have got an email. Let's try to fix all these things. Maybe by today we will fix these things. Okay. Yeah. So access to OpenIndex, all those things we will fix by today, tomorrow. So Suryansh also didn't get. Okay. Let's fix this. Okay. So we will take care of this. Okay. We'll attend to this and see that everything is in place by no, in a day or two. Okay. Good. So let's get started with today's lecture. So we are working on the syntax analyzer component of the compiler. Okay. So here, let me, yeah. So we are working on syntax analyzer. And it consists of two components. One is the lexical analyzer. The second component is the parser. Okay. So given a programming language, what do we do? The first thing that we have to do is we have to specify what is the micro syntax of the language. Okay. The micro syntax of the programming language, it tells us what is the structure of the words in that language. Okay, what is the structure of the words? What are the different parts of the speech available, etc. Whereas the macro syntax of the programming language, it tells us how different words come together to form a sentence, how different sentences come together to form a paragraph, so on and so forth. Okay. So, and the micro syntax we specify using context-free grammars, and the micro syntax we specify using regular expressions. Okay. So once we formally specify the micros and macro syntax of the programming language using regular expressions and context-free grammars, okay, then we move on to the next step, that is, how do we go about designing a lexical analyzer and a parser? Okay, so recall from the discussion from the last class, if we have a statement such as x plus y, it's an expression in a programming language, you may end up tokenizing this expression by saying, so is say this is the first token. Okay, it has two parts. One is the word or the lexeme. Okay, second is the token type, and together they constitute the token. This is the token. So this is the token type, and this is the actual word, or we also call it as lexeme. Okay, and then the second token is plus, the third token is y and id. Okay, this is tuple. Okay, and so while specifying this macro and macro syntax of a programming language, they are not independent of each other. Okay, so we have seen a couple of examples, but just to recap, so if you see, we have grammar G1 here and we have grammar G2 here. If you see here, so these two grammars pretty much look the same, but there is this minor difference in the microsyntax specification of these two languages, and it has impact on the corresponding macrosyntax specification. In the first case, if you see in the microsyntax, so here op is a terminal symbol, it is a token. Identifier is a token. Number is a token. Okay, so that means, so what happens is if you see the expression x plus y, okay, if you see the expression x plus y, the way this gets tokenized is x id and plus op and y id if you use this grammar G1. But the same expression x plus y, it gets tokenized in a slightly different form, that is x id plus and y. This is how it gets tokenized using the grammar G2. So if you see in grammar G1 has one less substitution rule when compared to grammar G2. Okay, it's because this particular substitution rule, expr of term, it got expanded into these two substitution rules here in grammar G2. So what I'm trying to bring to your attention is that there is a relationship between micro and macro syntax of a programming language. Okay, so some decisions that you make in micro syntax will have an impact on the macro syntax, and it's a design choice. Okay, so as I said, both grammars G1 and G2 are good enough grammars. Agreed that grammar G2 has one more substitution rule, but it is all right. Okay, this is not an issue. As against one grammar we have seen in the last class, which is pretty bad. Okay, excluding such design decisions, these are all good design choices available to you. Okay. So the other important thing is, in the last class we have seen that the syntax analyzer component consists of a lexical analyzer and then there is a parser. The lexical analyzer generates a stream of tokens, and these tokens will be consumed by the parser, and the parser will try to put together these tokens to see if they form a syntactically well-formed sentence in the language or not. Okay. But in practice, the way it happens is, it's not the case that after the lexical analysis phase is over, the parser phase kicks in. It's not the case. The way it usually happens is the parser kicks in and the parser asks the lexical analyzer, could you please give me the next token? Okay. And the lexical analyzer responds back by saying, hey, this is the token that is available in the string. okay, in the token stream. And then the parser consumes it. And then again, the parser goes back to the lexical analyzer and asks the lexical analyzer, could you please give me the next token? So the lexical analyzer and the parser, they kind of work in a interactive fashion. It is not the case that after the lexical analysis phase is over, the parsing phase kicks in. Okay, please remember this. Okay. Okay. So now, so given a programming language, and this is what is your first task in your project. So we want to design a lexical analyzer and a parser. And what is the first step in the design of lexical analyzer? We identify all the possible tokens. Identify all the possible tokens that can occur in any valid program. And this depends on the grammar that you are going to design for your programming language. Okay, so what it means is that there is a relationship between the microsyntax and macrosyntax. So the kind of tokens that you end up enumerating, it depends on the kind of grammar you are planning to design for your programming language. Okay, so you need to consult the grammar for the programming language to identify the tokens. Number two, second step is all the tokens that you have identified, you have to specify their lexical structure using regular expressions. That is the second step. And the third step is to either handwrite a lexical analyzer, okay, or handwritten lexical analyzer means you write code, you directly write code. Many times in your programming courses, you know, like you want to parse the command line options that are given to a program. So you end up doing multiple string compares to figure out what is the command line option that is provided to the program, right? So that is one kind of lexical analysis. So there you are handwriting a lexical analyzer. Okay, you either handwrite a lexical analyzer. The second option is you use a lexical analyzer generator tool such as Flex or JFlex or Antler. Okay, or Antler. That's what we are using in this course. Tool to generate the lexical analyzer. Okay. So, for example, in your in a C-like programming language, the possible words that can occur in a program in a C program is like int, float, while, all these keywords, right? So if you see here, all these keywords, so they are all possible words that can occur in the in a C-like programming language. Okay, keywords. All keywords, they form, they are possible words that you can find in any C program. And associated token type, so they stand for themselves. So the token type associated with int is int, the token type associated with float is capital float, so on and so forth. Okay, so, and the next kind of words that you can encounter in a C program are identifiers. Okay, identifier is like a noun in English language. What is the structure of an identifier? Like it should start with a letter and followed by 0 or more letters or digits. In the particular regular expression specification that I have given here, it doesn't allow digits in an identifier, but in C programming language, you know, like I think identifiers can contain digits, but an identifier should always start with a digit. Okay, so what you are seeing here, this is the lexical structure of the identifier token type, and it is specified using a regular expression. Okay, so now we will take a pause and ask this question. If you look at this regular expression, you know, like all these keywords, they are described by this regular expression. So if the compiler or if the lexical analyzer hits a keyword such as float in the program, should it classify float as an identifier or as a keyword? Okay, that's a question. So there is an ambiguity in the token specification here. So the way we resolve this ambiguity is, so in the specification, if so the token type we associate with a word, uh, it depends on where in this list of token types that particular uh, token type is listed. Like for example, float is listed before identifier. So float has higher precedence than identifier. So what happens is, like this float is classified as of token type FLOAT as against identifier. Okay. So this is a precedence rule that we have. Okay. So usually what we do is when we are specifying the lexical structure of a programming language, all the keywords are listed first, followed by the definition of identifiers, for example. The next token type is like, for example, integer literal. Okay. What is the structure of an integer literal? It is digit followed by 0 or more digits. Okay. Similarly, you can define floating point literal, so on and so forth. And then there are operators, okay, greater than or equal to, okay, equal to, left parenthesis, right parenthesis. So these are all different uh, token types that can occur in your programs, okay. And then again, if you see, there is a little bit of ambiguity here. So let's say if in your programming language you have a statement such as x greater than or equal to y, then how should we tokenize this expression? Okay, should we tokenize? So x is, this is all right. So x is an identifier, but then after that there is a problem. Should we tokenize greater than or equal to as greater than followed by equal to, or greater than or equal to as one token? Okay. So again, what we do is the rule that we follow is we try to find the longest matching word and give that as the uh, token. Okay, give it as the token. So greater than or equal to is the longest matching word. So we give that as the next token, as again as greater than followed by equal to. Okay. So this also has an implication. So this rule that try to extract the longest matching token from the input stream. So it is applicable in one more case also. For example, if you have an identifier such as inter, okay, this is an identifier. Then if you think about it, then so you may end up tokenizing this inter as int followed by er, okay. But then we will not do that because we try to match the longest matching token. Okay, so if you do this, then what happens is this gets tokenized into, there are two possibilities. So er followed by identifier, this is one possibility. The other possibility is inter identifier. Okay, so we tokenize it in the second way because we want to extract the longest matching token from the input. Okay, so these are the two rules. There are two ambiguities that you see. That is, the same word is matches the regular expressions corresponding to two different token types. In which case, the regular expression which is occurring first in the list, it takes precedence over the regular expression which is occurring later in the list. Okay, uh, that is one. The second idea is there are multiple ways to tokenize an input stream, in which case we try to extract the maximum word, okay, maximum matching word from the input stream. So these are the two rules that we apply in order to resolve ambiguities in the token specification or in the lexical specification of a programming language. Okay, so these are the two simple rules. Number one, return the longest matching lexeme or token. Number two, token types are prioritized according to their occurrence in the lex file. Okay. So what we do is, so as I said, we can, once the token specification, once we have arrived at the token specification, so this token specification, it can be yeah, specified in this particular syntax, okay? And then we can use tools such as Lex, Flex, Antler to automatically generate lexical analyzers. Like for example, your token specification, you can provide in a file called as lex.l or anything.l, and then you give it to a lexical analyzer generator. Okay, a lexical analyzer generator is a source to source translator. This is an example of source to source translator. Okay, and then it generates a C file. Okay, and this C file contains the actual scanner or tokenizer. Okay, this contains this. So it contains a function called as yylex and many other helper functions. This yylex function, what it does is it actually tokenizes the input. So when the parser wants an X token, it calls the yylex function, and the yylex function, it extracts an X token from the input stream and gives it to the parser. Okay, so what you do is you just take this lex.yy.c file and then you give it to a C compiler, you generate an a.out. So this is the actual executable scanner. Okay, and then you pass an input stream to this executable, and then it generates a sequence of tokens. So actually, as I said, we will not be using Lex or Flex in the course project, but nevertheless, take a look at it. So what happens is, if you take any Lex program, it consists of three parts or three sections. The first section is the declaration section. The second section is the translation rules section. This is where the actual lexical structure of the programming language is specified. And then third is a set of bunch of helper functions will be present, and that is the third section. Okay. So this is an example of a lexical specification for a for a C-like programming language. So here, the first rule here, if you see, it is in flower brackets WS. So what this means is, this is a nice way of specifying that this stands for, WS stands for white space. So if you see, white space is defined here in terms of delimiters. So essentially what happens is, this is equivalent to this, okay, /t/n plus. Okay, that means one or more occurrences of white space, tab, or new lines so they all together constitute white space. So when such white spaces occur in your programming language, you don't need to do anything, you just zap them. Okay, this is what you are doing. No action and no return. And if you see if, okay, if is a regular expression, it's an extremely simple regular expression. It describes only one word, that is if. If you see if, then there is a corresponding action that is written the token type if. Okay, this capital IF, okay, you see. So this is not a complete specification. The complete specification file you are not seeing on the screen, but there will be some kind of hash defined macro which says hash if is equal to some 30. That is the token type number associated with the if. Okay, it can be 30 or 31 or whatever it is, depending upon how many terminal symbols are present in your specification. Similarly, if you see then what you do is in the input stream, then you return a token type then. Okay, and if you see ID, Okay, so what is ID? So ID, if you see, it is letter followed by letter or digit 0 or more times. How is a letter defined? Letter is defined as A to Z, this one, and similarly digit is defined like this. So essentially this ID, so after all this expansion, what it gets transformed to is like this. So A to Z, A to Z, and then followed by uh, so what this means is your identifier can start with a capital or a small letter followed by uh, a letter or any letter or any digit, 0 or more times. And when you see when the lexical analyzer extracts an identifier from the input stream, it does this action. So if you see, this action is slightly more involved than the actions that we have seen before. So here there is something called as an install ID function that is being called. Okay. So this install ID is a user-defined function. Okay, that you can have, instead of install ID, you can have whatever other function, function you can have. But what this does is, this particular function, it enters the symbol, this identifier, into a symbol table. Okay, make an entry into symbol table. Okay, this is what this install ID function will do. Okay, and then after you make an entry of the identifier into the symbol table, then you return the token type ID to the parser, so on and so forth. Similarly, if you see a less than symbol, then what happens is you tell the parser that you have seen a relational operator, and the particular relational operator that you have seen is LT. Okay, so whatever this YYL function, right? So when the parser sees that the current token is a relational operator, it will go and check this YYL value to see what kind of relational operator it is. Okay, and all these things, these are very the particular notation, etc., that we are using. These are very flex specific, very lex and flex specific. You will find equivalent things in Antler also. Okay, you will find equivalent things in Antler also. So the lexical analyzer, so what it does is it takes the specification and it generates that lex.yy.c file, which contains the scanner or the lexical analyzer. Okay, and how are the ambiguities resolved? So two simple rules: return the longest matching lexeme, and token types are prioritized according to their occurrence in the lex file. That is, if the input stream contains a word such as if, the regular expression for word is occurring before the regular expression for identifier. So what happens is this rule takes precedence over this this rule. Okay, this is what happens. Okay, this is how ambiguities are resolved. Okay, so these are the two pattern matching rules. Again, to emphasize, always prefer a longer prefix to a shorter prefix. Okay, that is, if this is your input stream, and let's say this part is already tokenized, and so now the input pointer is pointing to this particular character. Let's say this is F, and if the next and then there is a function called get next token. Okay, in the lex parlance, this function is yvlex function. So what this yvlex function try to do is it always try to extract the longest matching prefix. Okay, it wants to extract the longest matching prefix. Okay, that's what it does. Like for example, if the word here is floater, sorry, let me if the word here is, let's say, FLOATER, ER. And if the parser asks for the next token, then what happens is you don't, the lexical analyzer doesn't stop here, doesn't stop with float and responds back by saying, you know what, the next token is float. But instead, it goes all the way till this point and then extracts floater as the next token in the input stream, and the associated token type is identifier. The second is if the longest possible prefix matches two or more patterns before the pattern listed first in the flex program. So these are the two rules. Okay. So now there is the question of handwritten versus auto-generated scanners or lexical analyzers. So in practice, many people still want to write scanners by hand. So the reason being, if you write your scanner by hand, it is possible to generate better error messages. Okay. Versus if you use auto-generated scanners by using tools such as Flex and Antler. Okay. But then, even if you intend to hand code a scanner, so writing down the specification and understanding the automata, and understanding, this is the overall structure, lexical structure of the programming language is useful. Okay, so even if you hand code and scanner, it is better to write the micro syntax of your programming language carefully. Otherwise, what happens is if you just start coding, the micro syntax of your programming language is indirectly embedded into your program, and it is hard to understand your program and from that elicit what is the microstructure of your programming language. Okay. So so this is one. In practice, like if you go to industry and if you're working on some project, it may not be worthwhile to hand code a scanner because you could be working in one project with a very limited set of clients or customers who know very well about the domain and things like that. So in which case, and your task is not so much user friendliness. You want to get the job done as quickly as possible. You got 2 days or 1 week time to write a parser for a particular configuration file parsing uh, task. Okay, so there, if you start writing, hand coding a scanner, it's too much effort. Okay, so there you can just go ahead and use the tool and use the generated scan. But if you think of compilers such as GCC, LLVM, etc., where the end user base is really large, okay, so maybe so 1 lakh people, 2 lakh people, or so many people use these compilers. So there it makes sense to take the extra effort to hand code a scanner so that it is efficient, number one. Number two, you generate good error messages to the end user. This is the case when the end user base is really large. Okay, so at least tens of thousands of people are using your tool. But if the user base is very niche group, then you may not want to invest so much time in hand coding a scanner for that particular job at hand. Okay, so I will take a pause now and see if there are any questions. If there are any questions, this is the time to ask. How do you, Prajwal Krishna has this question, how do you handle operator precedence? So we will come to operator precedence later, Prajwal. So we are not yet there. Okay, when we are studying the theory of parsing, now we are studying the theory of scanning. Okay, so at this point in time, operator precedence we cannot take care. Good question. Is it possible to modify the scanner code generated by an automatic scanner generator to generate better error messages? Usually it is hard, okay, because auto-generated codes, they will be very, very big in size, and no, doing some modification, just understanding them itself is a pain. Um, yeah, so it's usually difficult to modify an auto-generated scanner so that we can generate better error messages. Good thought though. Okay. Any more questions? All right, so let's get going then. So now what we have is, so we are given, the problem at hand is we are given the lexical specification of a programming language has a sequence of regular expressions R1, R2, R3, so on up to Rk, and associated with every regular expression there is some action that, so when you find a word in the input stream which matches any of these regular expressions, do the associated action. Okay, so this is what is the task. So your microsyntactic structure, your microsyntax is specified in this particular way. So what we do is we will solve this problem, the problem of designing a lexical analyzer in multiple phases. The first phase is, let's focus our attention on the simple task. Okay, so okay, let's pay attention to this simple task. So you are given a regular expression R, and we have to build a C function which checks whether an input string is described by the regular expression R. Okay, so this is the task at hand. So we are given a regular expression R, and from this regular expression R, we want to construct a function is R, which takes, let's say, a word, okay, and then so this function should return true if W belongs to, the language described by R, it should return an accept message, and otherwise it should this is yes, this is no, otherwise it should reject that input string W. That is the task. So, and we want to do it, we want to come up with an algorithmic approach to construct the function is R, okay, from the regular expression R. So what is the idea? The idea here is we start with the regular expression and we convert the regular expression into an NFA. Okay, so we know from your automata theory course how we can mechanically convert a regular expression into an NFA. And once the NFA is constructed, again we have an algorithm which converts that NFA into a DFA. Okay. What is NFA? NFA is non-deterministic finite automata, and DFA is deterministic finite automata. And then the next step that we do is we minimize the DFA, okay, so that the number of states in the DFA gets shrunk. And then finally what we do is we translate the DFA into an equivalent program function. That is the last step. And the time complexity of the resulting function is a big O of t, where t is the input string length. Okay. So its time complexity is big O of t. The important observation here is all these 4 steps, 1, 2, 3, 4, they can be done mechanically. They can be done algorithmically. You don't need to apply your brain. There is an algorithm to convert regular expression to NFA. There is an algorithm to convert NFA to DFA. There is an algorithm to convert, to minimize the DFA. And so once we have the DFA, we can algorithmically generate a program which simulates that DFA. Okay, and the time complexity of the generated program is big O of t, where t is the input string length. Okay, so for example, if you see here, we have a floating. This is the regular expression which describes a float literal. Okay, I hope you all understand or able to recognize that this regular expression that we have here, this describes a float literal. Okay, we have the decimal point here. So after the decimal point, you can have 0 or more digits, but before the decimal point, you need to have at least one or more digits. Okay. So, and the associated DFA for this the float literal is this. Okay, this is the DFA for the, so this is the DFA for the regular expression. Sorry, this is the DFA for the regular expression. Okay, great. And this DFA, this is the table representation, that this is the transition table for the DFA. The table that we are seeing here, transition table for the DFA. Okay. So once we have the transition table, okay, so we can easily, if you look at the code, this is float literal, okay. So there is this variable state. You start in the initial state. You start in initial state, and then you read one character of the input string at a time. And then if the current state is state, you read the next input symbol str, and then you go to the next state. And so at any point in time, so if you enter a error state which doesn't have any outgoing states, then you say a reject. But if you are able to successfully process, read the whole string, and you come out of this for loop, you see in which state you are in, and if you are in a final state, then then you return accept, otherwise you return reject. Okay, so you either accept or you either reject. So if you look at this code, an interesting thing about this code is pretty much independent of what regular expression we are talking about. So instead of is float literal, if the regular expression is an integer literal, and if you want to design a function or a program for int literal, this code, the template code or the boilerplate code that you are seeing on the screen exactly remains the same. What changes is only this next state function. And actually this next state function, okay, this also doesn't change. What only changes is the transition function table changes, accessed by the next state function changes from one regular expression to another regular expression. Okay. So this gives us your first approach for a lexical analyzer generator, okay, or automatic function generator. So the boilerplate code remains the same, okay. What changes from one regular expression to another regular expression is only the transition table accessed by the next state function. Not only that, of course, the set of final states also will change from one regular expression to another regular expression. But then the code doesn't change. Your set of final states you could be storing in some data structure. All that changes from one regular expression to another regular expression is the data structure. Okay. So you're all with me here? Are there any questions? Let's see if there are any questions. So Tanmay has this question: does time complexity of recognizing whether a word is in the regular expression or not depend on the size or complexity of the regular expression? So good question, Tanmay. So there are two costs that you should see here. The question that is being asked is, so there is a regular expression that is being given, okay? So from this regular expression R, so we generate this function is R, okay? So let's say this is, think of it as compile time or generation time. And after this is over, after this is all done, you use is_r function multiple times. Okay, you use is_r function multiple times and think of it as runtime. Okay, runtime is the time when the end user uses your is_r function. So the time complexity of this is_r function, it is just dependent on the word length. Okay, so it is going to be theta of t, where t is the word length. Okay. But going from R to is_r, so its time complexity, it is different. It will not be linear actually. It could even be exponential. Okay, so this time complexity is different. Going from R to is_r, it is actually independent of the word. It is dependent on the length of the regular expression. So here, this time complexity, it is dependent on the length of the regular expression R. Okay. So remember, when you move from the regular expression to construct an NFA, maybe the size of the number of states in the NFA may go from R to 2R, where R is the length of the regular expression. And when we go from NFA to DFA, the number of states in the DFA can blow up cubically, or in the worst case, to exponential number of states also. So the time complexity of moving from R to is_r is different from the time complexity of the generated function is_r itself. The time complexity of the generated function is_r, it is going to be linear, but the time complexity of this process that is going from the regular expression to the generation of is_r, it could even be exponential. Okay. Questions here? Does it answer your question, Tanmay? Just want to check. So how many of you are doing all right so far in this lecture? In this lecture, and so we are all connecting remotely, and I'm not exactly sure how you are able to follow the lecture, whether it's all right or not. Okay. Okay, I hope you are all doing good. Let's move on. So there is an alternate approach for generating, this is what is called as a table-driven approach for generating scanners. There is an alternate approach which is called as a direct coding approach. In the direct coding approach, what we do is we generate a spaghetti code like this. So associated with every state, there will be a chunk of code. So associated with state 0, we have the code here. Associated with state S1, we have the code here. Associated with state S2, we have the code here. So like for example, if you are in state S0, you check whether you have already consumed all the input. And if you have already consumed all the input and S0 is not an accepting state, so you reject. But on the contrary, so if you see, then if the string is not completely consumed, you read the next input, and if the next input lies between 1 and 9, then you say go to state S1. And if the next input character, if it is none of the characters 1 to 9, then you reject. So like that, again, when you go to state S1, you check whether the input is completely consumed, and S1 is not an accepting state. So if the input is completely consumed, so you end up rejecting the input string. On the contrary, if the input is not completely consumed, you see what is the whether the next string lies between the characters 0 and 9. If so, then what you do is you go to state S1, which means you jump back to the statement labeled S1. But on the contrary, if the next input character is I, then you go to state S2. Okay. If the characters are neither from 0 to 9 nor dot, then you reject the input string because you have encountered an extraneous character. Okay. So this is what is called as a direct coded approach. So usually generating scanners in this way, this is kind of more painful because you have to generate this code. Okay, generating this code, it's a lot of engineering effort. Automatically generating this code is a lot of engineering effort, as against the table-driven approach, where all you have to do is you just generate the table, the rest of the C code just remains the same. Okay. So software engineering wise, it's easy to design. I feel it is easy to design uh, table driven scanners. Sorry. I have to qualify this statement. When we take this approach, number one, you remember, one is a handwritten scanner. So usually handwritten scanners, they take the direct coding approach. Handwritten scanners, they take the direct coding approach. And since you manually write this whole code, you can generate error messages very nicely. You can embed error messages nicely in this code. But if you are taking scanner generator approach, that is, okay. So when you are taking scanner generator approach, you are using the tool at a different level. So actually you don't care whether what the scanner generator is doing. But from the scanner generator designer perspective, that is the person who is writing the flex designer. Who is a flex designer? The software developer who is writing the flex tool. From his perspective, he will be very happy to generate a table driven scanner, because all he has to do is he just have to take the regular expression and generate a transition table. Okay, so a flex designer or a scanner generator writer, he will be very happy to generate a table driven scanner as against generating a direct coded scanner where he has to generate this complex piece of code that you are seeing on the screen. Okay, but when you are hand coding your scanner, you naturally end up taking the direct coding approach, and that permits you to generate error messages nicely. If you recall the code that you have written to parse the command line options, that's what you do, right? So you try to have multiple nested if statements, and then you suitably embed error messages if you hit some problematic input arguments, etc. Okay. So this is a summary of today's lecture, that there are two ways of two ways of writing scanners. One is direct coded scanners, the other is table driven scanners. Table driven scanners are good for scanner generator writers, that is flex writers, lex writers, or antler writers, because they don't, all they have to do is they just have to generate a table. But generating direct coded scanners is painful. So, but they are useful for those who want to hand code the scanner, because they can suitably nicely embed good error messages in the code. Okay, so I will stop today's lecture here, and in the next lecture we will continue the discussion. We will what do you say? We will conclude the discussion on lexical analysis in the next lecture. The next lecture is on Saturday. Okay, that is all. Thank you. So if you have any questions, please stay back and ask. And I also have a request. I want to meet all the students in small groups. So those of you who don't have a class after at 11:30, no, if you can stay back, then we can have a brief chat so that I'll get to know you better. Okay, so I'm stopping the recording here.